Greetings, AP Chem. We are going to take our first foray into thermochemistry by taking a look at energy diagrams. And I think that this is probably the best way to start because it gives us kind of the general idea about how you get a change in energy from a chemical reaction in the first place. And then we'll kind of dive into actual numbers. So we're going to get into kind of the gist of it, and then we'll talk about the math. I think that makes things a little bit easier. So when we talk about energy changes, the best way to kind of think about a chemical reaction is to take a look at what we call an energy diagram. And an energy diagram, what it has is it has energy on your y-axis. So if you think about a vertical jump means that there's a rise in energy, or if there's a drop in energy. And when we think about our x-axis, it's the progress of the reaction. So that just means like from start to finish, or time, or whatever you want to call it. And so right now, this particular graph doesn't have any numbers, but we could, if you wanted to, put some numbers on our y-axis here. And if we took a look at them, the distance from the x-axis up to wherever this value here is the energy that your reactants start at. And that's like a potential energy. When we talk about potential energy, it's energy that's stored up and could be used for something if we could find a way to kind of unlock it. And so if we would have a value, let's say there was 75 here kilojoules, that means that our reactants have a value of 75 kilojoules. Okay. Now, reactants we know about. Products are down here on the back side of our reaction. And if we would measure the distance from the x-axis to this point using our numbers, if they had them on the y-axis, it'd be the energy of our products. And you're very familiar at this point with reactants and products. But there is this kind of transition that happens in all chemical reactions where you have reactants, and to have the reactants start reacting, we need to smash those things together. And when we smash those things together, they need to hit at the correct speed, the correct orientation, the right energy to make that happen. And if they don't have the right orientation, speed, energy, all that kind of stuff, the chemical reaction stays as reactants. And so what happens is when they do finally hit, they kind of connect in whatever way they're supposed to connect, and then they start to kind of break apart and stretch apart into a weird mishmashy combination of sort of your reactants, but also sort of forming your products, and that is called the activated complex here, okay? Now, the activated complex is like a transition state between your reactants and products. And what can happen is if we have an activated complex, but not enough energy to kind of get over this hump here, which we'll talk about in a second, you can actually have your reactants turn back into reactants. So your activated complex slides back down this hill. But if there's enough energy to get your reactants to the activated complex state and then down the hill, you're going to create your products, okay? And so the energy actual value of that would be from the peak here all the way down to your value here, which usually is 0. So that's the energy of my reactants, the energy of my activated complex, and the energy of my products. So like I had said before we get started, our reactants are our reactants, but then once they collide, they kind of form a transition state where we're sort of, turning into one thing, but leaving the state of another, and that's our activated complex. And then when they go over that hump, they separate and they turn into our products. So when we talk about our chemical reactions, you always have to think about them having two parts. And one part of the chemical reaction is always endothermic, and one part is always exothermic, no matter what. So we've talked about endothermic and exothermic. Endothermic means that the energy needs to go in to make something happen, and exothermic means energy comes out as a consequence of that thing happening. Okay, so when we break up reactants, to make those bonds break, you need to hit those things together, and that requires energy being input. And so that is an endothermic step always. Reactants require energy to break apart. To break those bonds, to physically rip them apart, you need to add energy, and that makes that an endothermic process. Now, What happens is you turn them into the activated complex, and that activated complex has a lot of energy. Everything's kind of agitated and very high energy. And then what ends up happening is that when you recombine them into your products, that drops the potential energy of that. So if you think about your reactants, I'm trying to think about how to show this to you the right way. I think it's backwards. So I've got my reactants. Then I jack them up by adding energy to them into that activated complex. When they reform, they settle down, and when they make those bonds, anytime you make a bond, it is an exothermic process, okay? So anytime you break a bond, you put energy in. Anytime you make a bond, you get a little bit of energy out, always. In a chemical reaction, then, the overall change in heat, or in the new term we've talked about, enthalpy, that change in energy that we get is the difference between those two steps. So if one is a big step and the other is a little step, you have either an overall endothermic or exothermic process. But every chemical reaction has an endothermic and exothermic part, and then the reaction tells you which side is bigger. And we will dig into that in just a little bit. So here's a beautiful little animation that we've got here that kind of shows us what I'm talking about. So if you think about your reactants here, the first thing we need to do is we need to get them all hot and bothered and smashed together and starting to break apart in that activated complex. Now, the energy that's required for that is something called the activation energy. So like I said, if it doesn't have a sufficient amount enough of energy, it's not going to happen. So it's kind of like a roller coaster. My little ball here has to get up, and if it doesn't have enough energy, it's going to roll back down the hill. When I have had the correct number of collisions, correct orientation, correct energy, all that kind of stuff, I roll down the hill. So this is the endothermic part of our process, because I got to put energy in to break bonds. So from reactants to activated complex, I am adding energy in to break those bonds. On the backside then, you can see it kind of rolls down an energetic hill here. What ends up happening is that when I turn back into my products and I reform, I get some of that energy back out. The difference between the energy of the reactants and the activated complex is called our activation energy. So if I had number values here, you could find the difference between these and then get that value, okay? Always remember, when you do any calculations using a graph, you're going to do your final minus your start. So we'll look at the final value minus the start value here. The difference between where your reactants and products are is the enthalpy change, or heat, for your reaction. So in the case of exothermic processes, and we'll get into this in a minute, exothermic processes have a negative change, and that's because we end low. Endothermic processes have a positive change, and we end high. We're going to get into that right now. So here's a graph for an exothermic reaction. You could potentially have to draw something like this, or alter a graph, or read a graph, so be aware of what you got to do here. So like I said, our reactants start off with one whatever energy value they have here, and then you need to apply your activation energy to get to the activated complex. Whatever the difference is between these two is your activation energy. Then in an exothermic process, what ends up happening is that the energy that you put in is less than the energy you get out. And what that means is that my reactants start off at a high energy, and my new combination of products is lower and more stable than my start. So if I have an exothermic process, if you think about this, I put in some energy to break my bonds apart, but I get a lot more back out. And the difference between those two number values for my actual energies is my change in enthalpy for my reaction, or that change in energy. If I would want to find this, I'd take the energy of my products minus the energy of my reactants. And because this is a lower number, you get a negative value. And that's why an exothermic process is negative. It's because the new combination of stuff that you make is just more energetically lower than what you started with. And that's good. Chemicals want to be lower in energy. Okay, so if you think about this, this is exothermic. We're going to go to endothermic next. I want you to kind of predict how you think this graph is going to be different. Think about where we're going to start, where we're going to finish, that kind of stuff, and see if you can predict it. Okay, that's literally coming up next. Was the endothermic graph everything you thought that it would be? Hopefully you predicted correctly. When we think about an endothermic process, we talk about heat going into it overall. So if you think about this as a two-step process, like all chemical reactions are, you are going to have your reactants at a specific potential energy. You put that energy in to make the activated complex. That is your activation energy, like we talked about. But what happens is when you reform your products are higher in energy than your reactants are. And so the difference here is your enthalpy change value or your energy change, but it's positive because I have a high number minus a small number. So when I talk about my endothermic reactions, what happens is you got to put more energy into breaking them than you get making the bonds. So energy in to break is not, or is greater than energy out for products. And so this is, like I said, not a super favorable situation. You should be able to look at a graph and know right away endothermic or exothermic. Okay. So like I said, exothermic, a little bit of energy in, but a lot of energy out. So a little in to break the bonds, but you get a lot out when you make the bonds. Endothermic is the opposite. A lot of energy in when you break them and only a little bit when you get them back out as products. So like I said, exothermic is more favorable, endothermic not quite as much. Now, the big trouble with all these is that you need to provide some sort of activation energy. That could be a spark, it could be you having to heat it, it could be any of those kinds of things, but you need to kind of get that thing going, provide a little oomph to start your reaction. That can make certain chemical reactions difficult. And one of the things that we do is we add something called a catalyst to make that go faster. You've probably heard of like enzymes or catalytic converters, those things, they all do the same thing. So what an enzyme or a catalyst does is they actually, if you think about this red line here as our normal graph, so this is our normal energy diagram, it is like lowering the activation energy. Your catalyst, what it does is it provides an alternate way to get to your product that takes less energy to make it get over there. So what happens is if we think about a catalyst lowering the activation energy, it means that at any specific temperature, more molecules can convert and turn into the activated complex and then the products. Think about it kind of like this. If you are needing to cross a mountain range, you could either go up and over the actual mountain, or you could take a tunnel and go through the tunnel and cut off, part of the mountaintop. So when we talk about using a catalyst, the catalyst drops that activation energy, and then more molecules have that energy at a lower amount of actual physical energy that you have to add in. So that is kind of the general gist with this. We are going to be taking a look at these graphs in your homework assignment. So if you have questions, please come and ask them. Otherwise, good luck on your homework assignment, and we will see you next time.